In the last video, we looked at how nature works in a manner in which it minimises quantities. And we said that the mathematics that we want to learn in order to understand this process is called the calculus of variations. Now what we're going to do here is we're going to state a basic principle. Now this is called Hamilton's principle. We're not going to go through any mathematical details here or derivations of this principle. We'll look at that later on in the course. We simply want to state this principle and also have a little look at the historical context and where this principle came from. Now Hamilton's principle tells us that a quantity I, which we will call the action, which is equal to the integral between 2 times t0 to t1 of some value L by dt is stationary. Now this here is Hamilton's principle. Now the value that we're interested in, L, is simply the kinetic energy minus the potential energy. When we see in mechanics that these terms tend to be written in the value T for kinetic energy and the value V for potential energy. So this might not mean an awful lot to you at the moment, but let's talk through and we'll see if we can understand what this is telling us. We said that nature tends to act in a manner in which it minimises quantities. Well, in fact, what happens is nature acts in a manner such that it minimises this quantity here, which we'll call the action. Now, whenever we use the terms minimisation, we're not actually correct in that, because it could be that this value of I, which we call the action, may well be not a minimum, but it may be a maximum. So for example, if it was a minimum, we could say we would have a minimum point here, but it could also be a maximum. So we could have a maximum point here. Now the other option is it would neither be a maximum or a minimum. In that case we would have a point of inflection. So we could have a point of inflection this way, and we could have a point of inflection this way. Now all of these four options here are encompassed in one word, and we encompass that in one word, which is stationary. So we can see here that the rate of change here is 0. That is the function is stationary at that point. The rate of change is 0. That is the function stationary. And also the function stationary here and here. So Hamilton's principle tells us that this value here, which we'll call the action, is stationary. It's not necessarily a minimum. But in dynamic systems, it turns out that the value that we are using here, L, which is called the Lagrangian, and the Lagrangian is nothing other than the kinetic energy minus the potential energy. And usually in mechanics, you'll see the kinetic energy written as T and the potential energy written as V. So for an actual dynamic system, the path that nature takes is the one that ensures that the action is stationary, so that this integral here is stationary. So let's look at a simple example of this down here. So let's say, for example, we were to fire a cannon. Then we know that the ball is going to fly off in some particular path. So if we make this the time axis, and we make that the height, then we know that we're going to have a certain angle at which the cannon sits. So let's say it's this angle here. And whenever we fire it, the cannonball is going to move off in some parabolic path, and it's going to land at some point here. Now if we were to do this same experiment again with exactly the same angle, then the cannon would land in the ball would land in exactly the same spot. And if we did this hundreds of times, it would still land in the same spot, so it would follow the same trajectory every time. Now we could ask the simple question, why is it that the cannonball travels in this particular trajectory? Why doesn't it fly off like this? Or like this? Or why doesn't it follow some complicated path, like, say, for example, this? Well, the answer to this question lies in Hamilton's principle. The cannonball will always go in the dynamic path that ensures that this value of the action is stationary. So in this case here, really what we're saying is that the difference between the kinetic and potential energies in this, for example here, are going to be minimized. So they're going to be minimized over the entire path. And whenever the value for the kinetic minus the potential energy is minimized over the entire path, then we know that this is the actual dynamic path that the cannonball will fly in, and this value for the action will, in this instance, be minimized. Now, the calculus of variations doesn't just apply to this particular principle. It's a much more general mathematical subject. And we may well not be using the Lagrangian. We can use any particular function within this. But the one that we're interested in mechanics and the particular applications of the calculus of variations are the calculus of variations applied to this particular term here, which is the Lagrangian. And we'll see that through the rest of the course. So let's go now and we'll have a little look at the historical nature of this Hamilton's principle. Now, as with all mathematics and science, the ideas don't just appear out of a vacuum. The people who are working on these ideas are standing on the shoulders of those who have gone before. Now, after Newton formulated his ideas of motion in the Principia, others who came after him reformulated these ideas in something that became known as the principle of least action. So the first person who historically has been linked to this principle of least action is Pierre-Louis Maupertuis. So in 1744 he put forward a principle of least action. So although the principle that he put forward is not in the same modern term as the Hamilton's principle, it does show that attempts were made at understanding the fundamental way in which nature works, and there was a comprehension that it did work in a manner in which some quantity was minimized. Now, Leibniz also formulated a principle of least actions, and his principle was based on the velocity squared, as opposed to the Maupertuis one, which was based on velocity. Now, a debate did rage through the 19th century in science as to who could claim to be the first person to envisage the idea of some all-encompassing principle of nature. And the two proponents were Leibniz and Maupertuis. But historically now we tend to look at Maupertuis as being the initial instigator of these ideas. Now, Leonhard Euler formulated some of the mathematics that are required in order to solve what are now known as variational problems, but he also put forward his own basic physical principles of dynamics as well. Now, arguably his most important derivation in this field is something that we'll look at whenever we do the calculus of variations, which is called the Euler-Lagrange equation. But also remember that Euler is standing on the shoulders of those who have gone before him as well, for example, Newton, Fermat, the Bernoulli twins. So the ideas that he came up with for variational calculus didn't just appear out of a vacuum. Joseph Lagrange reformulated the work of Euler into a purely analytic form, opening up the modern era of the calculus of variations. He also applied this new mathematics to mechanics and dynamics, and in doing so he really created the modern form of analytic mechanics. Then William Hamilton formulated the modern form of the principle of stationary action, which is now called Hamilton's principle. So Hamilton's principle is not just some historical crusty physics, it is alive and well at the heart of physics today, and it is applied in cutting-edge scientific research. So for example, when quantum mechanics was first formulated, it was formulated partly through Hamilton's principle and the application of the calculus of variations. And Hamilton's principle can be applied to electromagnetics, to special and general relativity, and in fact, if any new theory on physics is created, one of the first questions that would be asked is, how does this apply to Hamilton's principle, and what exactly is the function which we can call the action in this new theory? So this has been just a light introduction to Hamilton's principle, and hopefully I've put it into some historical context. The original principle put forward by Maupertuis was in 1744, and the final Hamilton's principle was created in 1834, so some 90 years. So it shows that these ideas don't appear out of a vacuum, and each individual is standing on the shoulders of those who have gone before. One other note to finish on is that you'll sometimes see Hamilton's principle also called the principle of stationary action. You'll also see it written as the principle of least action and sometimes the principle of minimal action. Now, throughout the rest of this course, we'll simply use Hamilton's principle, and Hamilton's principle will encompass all of these other names. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.